Welcome to lecture 37 on plant design and economics. In this week, we are talking about synthesis of separation systems, and in today's lecture, we will consider selection criteria for separation methods. Now, synthesis of separation systems involve the separation methods. So, you have to select separation methods along with energy separating agent and mass separating agent. We have to select separation equipment and then optimal arrangement or sequencing of this equipment, and finally, optimal operating conditions such as temperature, pressure for the equipment. So, this is what we mean by synthesis of separation systems. Now, there are several industrial separation methods. In our previous lecture, we have given you a table which involves certain basic informations about these commonly used industrial separation methods. Now, how do I select a particular separation method? So, what should be criteria for selection? So, this is what we are going to discuss in today's class. First, the criteria for selection of a particular separation method may be based on the phase condition of the feed. The phase condition of the feed may be a vapor feed, a liquid feed or a solid feed. If the feed is vapor, then we can select the separation methods such as partial condensation, which is opposite of flash or partial vaporization, distillation under cryogenic condition, gas absorption, adsorption, gas permeation using membranes, desublimation. If the feed is liquid, we can consider flash, distillation, both ordinary distillation, azeotropic distillation as well as extractive distillation, stripping, liquid-liquid extraction, supercritical extraction, crystallization, adsorption, membrane-based separation processes such as dialysis, ultrafiltration, reverse osmosis, pervaporation, etc. If the feed is in solid state, it can be a slurry feed or it can be dry solid feed. If you have a slurry feed, we can perform filtration or centrifugation to obtain wet cake, and then the wet cake can be separated into vapor and dry solid by method of drying. On the other hand, if we have dry feed, leaching can be used with a selective solvent. Now, we will define a separation factor which will guide us for selection of separation method. The separation factor defines the degree of separation that can be achieved between two key components of the feed. The separation factor for separation of component 1 from component 2 between phase 1 and phase 2 for a single stage contacting is defined as shown. Note that the separation factor has been defined as a ratio of two ratios. So, in the numerator you have concentration of species 1 divided by concentration of species 2 in the phase 1, and in the denominator you have concentration of species 1 divided by concentration of species 2 in the phase 2. So, it is a ratio of two ratios. we can use concentration, we can use mole fraction, or you can use mass fraction. So, in general we can say that the separation factor can be defined as a ratio of two ratios which indicates the composition of two species in both numerator and denominator. So, in the numerator you have composition of species 1 by composition of species 2 in the phase 1, and in the denominator you have composition of species 1 by composition of species 2 in phase 2. If phase 1 is to be reached in component 1 and phase 2 needs to be reached in component 2, then according to the definition of the separation factor, you can conclude that the separation factor must be large. Note that except for the membrane based separation processes, the extent of mass transfer in other processes are limited by thermodynamic equilibrium. So, the value of separation factor is limited by thermodynamic equilibrium, of course, except for membrane based separation processes where the exiting phases are not in thermodynamic equilibrium. Now, once we have selected the separation factor, we have to select a separation method with high separation factor. As we discussed, the separation factor is generally limited by thermodynamic equilibrium. For example, in the case of distillation, let us denote phase 1 to be the vapor phase and phase 2 to be the liquid phase. The compositions can be expressed in terms of mole fractions. In that case, the limiting value of separation factor is given in terms of vapor liquid equilibrium ratios or K values as this. So, separation factor is y 1 by y 2 divided by x 1 by x 2. So, y 1 is the mole fraction of species 1 in the vapor phase, y 2 is the mole fraction of species 2 in the vapor phase. Similarly, x 1 and x 2 represent mole fractions of species 1 and 2 respectively in the liquid phase. Note that this ratio can be expressed as K 1 by K 2, which are K values, and K 1 by K 2 is nothing but relative volatility. In general, the components 1 and 2 will be so designated such that the value of the separation factor is greater than 1. So, the larger the value of separation factor, the more feasible is the particular separation operation. So, according to the definition of our separation factor, the high value of the separation factor will go in favor of that particular separation factor. So, we will tend to select separation process or separation method with high separation factor. Now, we have to take certain cautions as well. While we select a high value separation factor, we should keep in mind that we need to preferably avoid extreme conditions for temperature, pressure, as well as sometimes we should avoid excessive use of mass separating agent. Why? Because the extreme temperature may require refrigeration, which is an expensive option. The extreme temperature may also damage heat sensitive materials. Extreme pressures may require gas compression or vacuum, again expensive options. High mass separating agent concentration may require expensive recovery method for the mass separating agent. Note that even if your separation process can be achieved in a single piece of equipment, but whenever I use mass separating agent, there has to be additional separation process for recovery of the mass separating agent, so that you can recycle it. So, excessive use of mass separating agent should be avoided in those cases where the recovery is very expensive. In general, operations employing an energy separating agents are economically feasible at a lower value of separation factor than are those employing a mass separating agent. So, let us follow a rule of thumb or heuristic or guideline. We will always try distillation first, provided vapor and liquid phases are readily formed. So, if vapor and liquid phases are readily formed, we will always try distillation first as the preferred method of separation, liquid-liquid separation. Now, let us consider separation factor for ideal liquid vapor solution and moderately non-ideal liquid solution. When a multi-component mixture forms nearly ideal liquid vapor solutions and the ideal gas law holds, the relative volatility and K values can be readily estimated from the vapor pressures of the species involved. Thus, the separation factor for vapor liquid separation operations employing an energy separation agent such as partial evaporation, partial condensation or ordinary distillation can be given by ratio of vapor pressures of the species involved. For example, separation factor alpha between 1 and 2, species 1 and 2 will be equal to vapor pressure of species 1 divided by vapor pressure of species 2. When the components form moderately non-ideal liquid solutions such as hydrocarbon mixtures or homologous series of other organic compounds, we can use equation of states to estimate separation factor by use of fugacity coefficients. The commonly used equation of states may be SRK equation as well as Peng-Robinson equation. So, for moderately non-ideal liquid solutions, the separation factor alpha 1 2 can be represented by ratios of fugacity coefficients. Note that in the denominator you have the fugacity coefficient of component 1 in the liquid phase divided by fugacity coefficient of component 1 in the vapor phase, and in the denominator you have the fugacity coefficient of component 2 in the liquid phase divided by fugacity coefficient of component 2 in the vapor phase. Now, there are liquid vapor separation processes where we use mass separating agents. In fact, use of mass separating agents can enhance the separation factor. Now, when you use mass separating agent, it may cause the formation of non-ideal liquid solutions. For example, in case of azeotropic distillation or extractive distillation, we use mass separating agents. So, when use of mass separating agent causes the formation of non-ideal solutions, but we operate at near ambient pressures, we can apply modified Raoult's law, and then the separation factor given by relative volatility can be estimated by use of activity coefficients. Note that the separation factor for non-ideal liquid solutions has been expressed in terms of activity coefficients of component 1 and component 2 and the vapor pressures of component 1 and component 2. So, gamma is the liquid phase activity coefficient, gamma 1 is the liquid phase activity coefficient of component 1, gamma 2 is the liquid phase activity coefficient of component 2, and P 1 and P 2 represents the vapor pressures. Now, how will you obtain these activity coefficients? The activity coefficients can be obtained by use of various thermodynamic models such as Wilson model, inertial model, uniquark model or unified models. Remember that the activity coefficient is a very strong function of mixture composition. Here the inertial equations which establishes the correlation between the liquid phase activity coefficient gamma I for component I with the liquid phase mole fraction of component in the X is shown. Here all the summations are need to be made for all the components present in the mixture. So, if we consider there are n components present in the mixtures, all the summations runs for 1 to n. Here x represents liquid phase mole fractions, gamma I represents liquid phase activity coefficient for component I, and then there are several binary parameters. The relationships are shown here. Now, some of the binary parameters such as A, B, C, D, E, F, they can be found in the literature for the particular system you are handling, if it has already been reported in the literature. Otherwise, these values can also be regressed from the experimental data on thermodynamic equilibrium. Inertial thermodynamic model can be used for generation of vapor liquid equilibrium data as well as liquid liquid equilibrium data. So, similar equations are available for Wilson models, uniquark models, unified models, etc. So, such a thermodynamic model can be used to estimate the liquid phase activity coefficient and then the separation factor for the non-ideal liquid solution can be obtained. Now, when we talk about liquid liquid separation, the separation factor is referred to as selectivity. So, when mass separating agent is used to create two liquid phases such as in case of liquid liquid extraction, the separation factor is referred to as the relative selectivity, and the relative selectivity usually denoted by beta can be defined as shown between components 1 and 2. So, again these are the ratios of activity coefficients of two components and in two phases. Here phase 2 is usually the MSA rich phase and component 1 is more selective for the MSA rich phase than is component 2. In general, operations employing an energy separating agent are economically feasible at a lower value of separating factor than those employing an mass separating agent. Usually, mass separating agents for extractive distillation and liquid-liquid extraction are selected according to their ease of recovery for recycle and to achieve relatively large values of separation factor. So, the selection of mass separating agent should be based on mainly two considerations. One is ease of recovery, second is enhancement of the separation factor. Such mass separating agents are often polar organic compound. For example, furfural is used for separation of N-butane from 2 butenes. This is what we have seen in the separation that we discussed, multi-component separation we discussed in our previous lecture. Sometimes the mass separating agent is selected in such a way that it forms one or more homogeneous or heterogeneous isotopes with the components in the feed. For example, consider the separation of acetic acid and water mixture. Here we add N-butyl acetate as mass separating agent. Upon addition of N-butyl acetate, a heterogeneous minimum boiling azeotrope of acetate and water is formed. We can take the azeotrope overhead and then separate acetate and water layers and then recirculate the acetate. Now, let us look at the importance of multi-stage operations. Generally speaking, the value of the separation factor is much lower than that required for achieving very sharp separation and for achieving the specified product purity. But the application of efficient countercurrent flow cascades of many contacting stages such as distillation operation can frequently achieve specified sharp separations. Note that the separation factors that we defined was based on single contacting stage. So, the value of the separation factor that we obtain will generally be much lower than that required for achieving sharp separation and than that required for achieving the desired specification on product purity. However, when we perform efficient countercurrent cascades of several contacting stages, we can frequently achieve sharp separations. For example, we generally obtain sharp separation in distillation operations, unless they are very close boiling mixtures. Let us say you have this given task. We have a mixture of 60 mole percent propylene and 40 mole percent propane. We want to separate it into 99 mole percent propylene and 95 mole percent of propane. We want to perform this separation at 290 psi absolute. A mass balance will tell you that 99 mole percent of propylene in the product stream is equivalent of 58.5 mole percent of feed. Similarly, 95 mole percent of propane in the product stream is equivalent to 41.5 mole percent of feed. Now, if I want to perform this separation, we first see that relative volatility is 1.12. a single equilibrium vaporization at 290 psi absolute to produce 58.5 mole percent vapor will have the product composition which is as follows. In the vapor phase, you will have 61.12 mole percent propylene, and in the liquid phase you have 51.36 mole percent propane at 51.4 degrees Celsius. Note that the product that we obtain using a single equilibrium vaporization is much less than the separation task that was specified, which is 99 mole percent propylene and 95 mole percent propane. So, single vaporization, single equilibrium vaporization cannot achieve this. However, we can perform counter current cascade of contacting stages in a simple distillation column, and we can achieve this separation. It will require 200 trays and high reflux ratio of 16, but we can achieve this sharp separation. So, when do we perform single stage operation? Single stage operations such as partial vaporization or partial condensation with use of an energy separating agents are employed only if separation factor between the two key components is very large, or if a rough or partial separation is needed. Then we can think of performing a single stage operation. Again, consider the separation of an equimolar mixture A and B. So, 50 mole percent A, 50 mole percent B, and if you want to separate it into 99 mole percent A and 99 mole percent B, the required separation factor for a single stage partial vaporization would be 10,000, which is very large. At low values of separation factor, say in the range of 1.05 to 1.10, the ordinary distillation method may still be the most economic choice for separation process. The use of mass separating agent may enhance separation factor. For example, extractive distillation. The separation factor can be enhanced by use of a mass separating agent, and your enhancement be to the extent that this process will be more economical than ordinary distillation. It is possible. Now, the plot shows you on the x axis we have plotted the relative volatility for ordinary distillation. So, separation factor for ordinary distillation, and in the vertical axis we have minimum relative volatility required for consideration of extractive distillation or minimum selectivity required for consideration of liquid extraction. This plot has been obtained on the basis of equal cost consideration. This plot will guide us to consider whether extractive distillation or liquid extraction will be more attractive, or when it will be more attractive compared to ordinary distillation process. So, when he can perform a particular separation using ordinary distillation, extractive distillation as well as liquid extraction, such plot will be helpful to figure out what should be the chosen process. For example, let us consider the separation factor equal to 2 for ordinary distillation. Then, if I want to use extractive distillation, the separation factor obtained by extractive distillation must be say as high as 3.3 or so. And if I want to use liquid extraction in place of ordinary distillation, the selectivity for the liquid extraction process should be as high as 18 or above. Then only the extractive distillation or liquid extraction will be more attractive or acceptable alternative compared to ordinary distillation. Similarly, when the separation factor for ordinary distillation is 3, note that the separation selectivity, which is separation factor for liquid extraction, has to be very high, I think in the range of 70 or so. So, such figure based on equal cost consideration will guide us to select appropriate method. Separation factor for absorption stripping. Unless values of separation factor are about 10 or above, absorption and stripping operations cannot achieve sharp separation between two components. Nevertheless, these operations are used widely for preliminary or partial separations where the separation of one key component is sharp, but only a partial separation of the other key component is adequate. So, when you are happy with sharp separation of only one key component, then this can be used. The degree of sharpness of separation is given by the recovery factor, where the recovery factor is defined as moles or mass of component I in the product phase divided by moles or mass of component I in the feed phase. Crystallization, when performed carefully, can achieve very high purity. Consider the separation of a mixture of metaxylene and paraxylene. Paraxylene used for polyethylene terephthalate, PET plastic bottles and polyester fiber. Metaxylene is used for production of isophthalic acid, is an important ingredient in polymerization industry, polymer industries. Metaxylene is also used in pharmaceutical industries. So, this is metaxylene and this is paraxylene. Now, if you look at the physical properties, particularly boiling point and melting point of this metaxylene and paraxylene, we see that the difference in normal boiling point is less than 1 degree Celsius, whereas difference in melting point is more than 60 degree Celsius. So, ordinary distillation is definitely not a suitable choice. The separation factor is only 1.02, and to produce relatively pure products from an equimolar mixture of the two isomers of paraxylene and metaxylene, we may require a distillation column with more than 1000 stages and a reflux ratio as high as about 100. However, if we use crystallization, the separation factor is almost infinity, because nearly pure paraxylene can be crystallized. However, the mother liquor contains at least 13 mole percent of paraxylene in metaxylene, because this corresponds to the limiting eutectic composition. The separation factor for adsorption depends on either differences in the rate of adsorption or adsorption equilibrium. For equilibrium adsorption, the same definition of separation factor applies, that is the ratio of two ratios which are composition of component 1 by component 2 in the phase 1 divided by composition of component 1 divided by composition of component 2 in the phase 2. Now, in case of adsorption, the concentration that are at equilibrium are concentration on the adsorbed layer within the pores of the adsorbent and concentrations in the bulk fluid external to the adsorbent particles. So, these two concentrations correspond to those phases 1 and 2 in the definition of the separation factor. When you have a very dilute mixture, you have only a small amount of one component present in the mixture. In such a case, changing the phase of the components in high concentration should be avoided. In such a case, adsorption, stripping or selective adsorption is more appropriate to remove the minor component, that means the component which is present in a very small amount. Adsorption is particularly effective because of the high selectivity of the adsorbents. It is widely used for purification where small amounts of solute are to be removed from a liquid or vapor feed. Now, let us talk about separation factor for membrane based processes. The separation factor is governed by relative rates of mass transfer in terms of permeabilities rather than by equilibrium consideration. So, separation factor here we define as permeability of species 1 divided by permeability of species 2. In most cases, the value of the separation factor must be established experimentally. Membrane separation processes should be considered wherever we consider adsorption methods as a possible separation process. Typical separation factor for gas separation using membrane is about 6. This separation factor is not very high for achieving sharp separation. However, this is good for achieving partial separation. Membranes are either porous or non-porous. If porous, the permeability is proportional to the diffusivity through the pore, and if the membranes are non-porous, the permeability is the product of the solubility of the molecule in the membrane and its diffusivity for travel through the membrane. Supercritical extraction. Supercritical extraction uses the solvent power of a gas at near critical conditions. Carbon dioxide is considered as a green solvent. At supercritical condition, it has very high solvent power. It has very enhanced solubility. Its critical temperature is 31.1 degrees Celsius and critical pressure is 73.8 bar. So, if you notice that the critical temperature is very near to ambient temperature, and this makes carbon dioxide is a very attractive solvent under supercritical conditions for heat sensitive materials. Supercritical extraction with carbon dioxide is the preferred method for removal of undesired ingredients from foodstuffs. It is also frequently used for extraction of phenolic compounds from plants. In recent years, the supercritical extraction using carbon dioxide is being increasingly used in pharmaceutical industries. The separation factor is difficult to estimate from use of equation of state, and the separation factor is best estimated or determined rather from experimental data. Similarly, for liquid-liquid extraction or leaching also, the value of separation factor is best determined by experiment. So, to conclude separation criteria, we state that the purpose of separations are purification of species or group of species, removal of undesired constituents, recovery of constituents from subsequent processing or removal. So, the broad purposes of separations are purification of a species or a group of species, removal of undesired constituents, and recovery of constituents for subsequent processing or removal. In case of purification, the use of a mass separating agent may avoid exposure with an energy separating agent to high temperature that may cause decomposition, particularly for heat sensitive materials. In some cases, removal of undesirable species together with a modest amount of desirable species may be economically acceptable. Likewise, in the recovery of constituents for recycle, a high degree of separation from the products may not always be necessary. With this, we stop our discussion here.